Hello everybody. In this video, we are going to go over regression loss functions in deep learning. There are two commonly used loss functions, mean squared error and mean absolute error. So let's first understand the definition of these two terms, and then we will learn how to implement them using two different methods. First of all, we will implement them using low-level TensorFlow functionalities, and then we will implement them using the API or high-level API provided by TensorFlow, which will be just one line of code. But first, let's understand what these terms mean. So the first one is mean squared error. There are three pieces to this expression. One is mean, squared, and error. So if you look at this expression, we have two vectors, y and y hat. The y values are basically true values, and y hat are predicted values. And these could be anything, but just to give you an example, these could be outputs of a neural network. Y is the true value and y hat is the predicted value. And both of them are vectors of elements n each. So the vector y is actually y1, y2, all the way to yn. Similarly, the vector y hat is y hat 1, y hat 2, all the way to y hat n. These are two vectors. What is the error between the two vectors? Error is nothing but the difference between the two vectors. So the error between vector y and y hat is nothing but y minus y hat. So that's the error. Second, the term is squared. Let's go from, right to left. So we have already seen what is the error. Error is the difference between y and y hat. Squared error. Squared error is nothing but element-wise squaring of this error vector. So we have the error vector, which is nothing but y minus y hat, and then we square every term of this error vector. And you can see this is what we are doing here. And the final thing in this expression is mean, which means that we are taking the average of all these error terms. So here, the squared error terms, we are adding them all together and dividing by n. So the expression mean squared error is basically the three things that we just did. All right, so this is pretty easy to implement. If you go and look at this, this function, what we are doing is it takes in two values, y true and y pred for predicted value. We are converting them to tensors, and then we are taking the difference of the two terms, as I had mentioned before. We are squaring the resulting vector, all the elements, element-wise, and then we are taking the mean of all the elements of this squared error. And that's the value we return. Very simple. Now, we can put some real values here. If you put in 0, 1, 0, 0 and 1, 1, 1, 0, you will see an MSE or mean squared error of 0.5. All right, so far so good. Nothing very complicated. Now let's understand what is mean absolute error. As you can predict, there are three terms in this expression. The error term, which is basically y minus y hat. The second term is different. It says absolute instead of squared, which just means that we are taking the absolute value of the error. So you can see here the absolute value, and then we have the mean. So we are adding all the absolute values, dividing them by n to find the mean absolute error. Again, if you look at this function, it is pretty straightforward. We are converting the two vectors into tensors, and then we are taking the absolute value. This is the only difference here of the error term. And then we are taking the mean and returning the mean absolute error. You can pass in some values and see what they return. Now, one thing to note between the two is mean squared error and mean absolute error. They differ in how they treat outliers. What does it mean? Let's look at an example. You can see here that we have y true. Most of these values, the difference is 1 or 0. But the last value is very different. We have seen that the last value, the true value, and the predicted value differ by 5, which is large. It's an outlier. Now, this one element is going to spoil the whole calculation. You can imagine that you could have a very long vector of 100 elements, and 99 of them are good. The predicted value matches the true value, and one of them is completely off. Let's say it is off by 10 times of the other vectors, of the other errors. Then that one value is going to mess up the entire error score. So that's the downside of using mean squared error. And you can see here that one value here is messing up the MSE. This is 6.25 compared to 1.25. So MAE, or mean absolute error, is robust to outliers, whereas MSE is not. MSE has some nice properties because it is this nice and smooth function, and whenever we have nice, smooth, continuous differentiable functions, it is good for numerical calculations. But the price we pay is that it is not very robust to outliers. So it depends on your application. Sometimes we expect outliers in our application, and in that case, we should be using MAE. Otherwise, typically, we could simply use MSE. So in the previous section, we implemented mean squared error and mean absolute error using low-level TensorFlow functions. But typically, we do not do that. We use loss functions that are defined in Keras, and it's just one line of code. For example, here we have the true and predicted values. We simply do tf.keras.losses.mean squared error, and we get the mean squared error. So if we run this thing, you can see that it is producing the same result. Similarly, we run this thing and it produces the exact same results as before. So typically, we never use the first method that we had shown, because why use it when TensorFlow already implements it in keras.losses. So we use keras.losses.mean squared error and keras.losses.mean absolute error to calculate these values. That is all I wanted to cover in this notebook. Thank you.